Okay, let's do the second example. The second example, we try to compute this integral. The integral from 0 to infinity sine x over x dx is pi over 2. Okay, so this function, first of all, if you consider naturally from the previous example, you will consider possibly. You may choose the sine z over z. I'm not saying it's not possible, but if you really do the computation, you will see that's not extremely simple. Okay, so we will not choose this function as our analytic functions with poles. We will choose another one. Instead of choosing sine z over z, we choose f of z equal to e to iz over z, e to iz over z, right? So we're going to choose this one. This one is a little bit better. It's a little bit better. And you will see that eventually this actually fits our construction of circles, closed rectifiable curves, because of the Euler's identity. Remember that Euler's identity, sine x. Sine x is what's that? It's a e to ix minus e to negative ix over 2i, right? Over 2i. Okay, so later we will use it. Okay, so now let's choose f of z as a e to iz over z. Then this one, f, has a simple pole, a pole with order 1. Pole at z equal to 0. Okay, and then we construct a closed rectifiable curve, and it has a simple pole. This time we try to avoid this pole. So you have 0 here. Then we draw a detour, a semicircle detour, and a bigger semicircle. So this is negative r, this is capital R, negative capital R. This is called little RC, C little r and C capital R. Okay, C little r, C capital R. And the curve gamma is the interval negative r, negative little r, union CR, negative orientation. Clockwise, CR clockwise, union little r, capital R, and union C capital R, positive orientation. Counterclockwise. So here this is counterclockwise, this is clockwise, this one. So the whole thing fits together. Okay, and you see here we avoid this the unique pole, so the integral f along gamma is equal to 0. The Cauchy theorem, whenever the function is totally analytic inside, then the integral is 0. Okay, uh, integral 0, and this curve consists of 4 parts, so we are going to write them in 4 different parts. So you have, let's follow the textbook order. This one from little r to capital R. Then you have a e to ix, they are reals. So and from along this bigger semicircle. Sorry. See capital R, then e to iz over z dz. And then back here it's plus negative capital R negative little r e to ix x dx, and plus e to small r, it is e to iz over z dz. Okay, so that's the part by part integrals. And this part we are going to use the variable substitution. Check here, from negative capital R to negative little r e to ix over x dx. You just let y be negative x. Y is negative x, then negative y is x, dy is negative dx. With this substitution, okay, so you have negative sign here in the denominator, a negative sign from the dx. They are cancelled, but you want to exchange the r and the little r, then you have a negative sign e to I. And then these two things, put them together, they share the same unit, same limit. So it's e to ix minus e to negative ix over x. Remember, those variables are dummy variables. So they don't. You can just write them as whatever letter you like. So here we use x. And e to ix minus e to negative ix is the twi. Yeah. Right? So that is the way to get it. And later we will see it. Naturally, we will let capital R approaches infinity, little r approaches 0. Okay, so we will let capital R approaches infinity and little r approaches 0. So then this is the situation. Now let's check how do we evaluate. Well, we still have a long time, long process. The first and the third, they will contribute the original integral, sine x over x integral from 0 to infinity, with the coefficient twi. And let's study the second and the fourth. So so keep this in mind. It's integral e to iz over z dz gamma, not gamma, c capital R. Remember, if we let, they are the semicircle e to I theta. Z is R E I theta. dz is R I E I d theta. We had this before. Whenever you have a semicircle centered at the origin, you will always have this. And this is a z. So dz over z is I d theta. This is a fixed setting. Whenever you have a semicircle centered at the origin, dz over z is I theta. So you have dz over z is I theta. So if we put Ab's value, it's going to be I is here. Integral. It's a positive orientation. It's from 0 to pi. Semicircle, upper semicircle. Check here, upper semicircle, the argument is always from 0 to pi. And this is EI theta, EIZ. So you have EIZ, Z is this, REI theta. Okay, and dz over z is I d theta. I d theta. dz over z is I d theta, and EIZ is this part, and from 0 to I. Okay, and then Ab's value I disappear. I give you 1. So it's less than or equal to, you also put the Ab's value into into it. So you have integral 0 to pi, Ab's value EI R EI theta d theta. Okay, so let's check it. Remember that EI, let's do it step by step. So REI theta is R cosine theta plus IR sine theta, and times I is negative R sine theta plus IR cosine theta. And put exponential function E so you have E negative R sine theta times E IR cosine theta. And then when you put Ab's value, only this term appears. This term give you 1. Ab's value 1. Ab's value give you 1. So this internal part is E to negative R sine theta. Okay. E to negative R sine theta. Okay. Then let's check. We want to estimate it. We want to estimate this value. How do we estimate the value? This part is very tricky and technical. We know that this is a continuous function. So for delta, sufficiently small, for sufficiently small delta, the exponential function e to negative r sine theta. This is a positive. When I put a negative sign, it will be negative, right? R sine theta, theta is between 0 and pi. It's a positive number. With negative sign, it's a negative. Negative number means it's in the denominator part. And when you have theta close to 0 and pi, when theta close to theta close to 0 and pi, then sine theta is close to 0. Sine theta close to 0, this negative value is a maximum, right? It has a maximum value. So this one has the maximum value. E to negative r sine delta. And this part is increasing. You choose a you understand? So you have the maximum value at delta. Okay, so now let's try to break this integral into two parts. Yes, two parts. Two parts is like three parts technically. From 0 to delta, e to negative r sine theta d theta, and from delta to pi minus delta, e to negative r sine theta d theta, and plus pi minus delta to pi, e to negative r sine theta d theta. Okay? And this one is at most 1. E to negative r sine theta is at most 1. So it means you integrate less than 1, integrate less than 1. This distance is delta, so it's less than or equal to 2 delta. And then plus integral from delta to pi minus delta, e to negative r sine theta d theta. Correct? Let me see if I'm making sense or not. Sine function is an increasing function. You choose a small delta. The largest possible value of exponential negative r sine theta. Yes. Yes. So let's check here. We are talking about the right. Now I understand. We're talking about the maximum value over this interval. check here, over, I lost my mind for a few seconds. Over this interval, sine theta is always greater than or equal to sine delta, because you see here, it's above the curve. So sine theta is greater than or equal to sine delta. So negative r sine theta is less than or equal to negative r sine delta. And then you take the exponential, so e to negative r sine theta is less than or equal to e to negative r sine delta. So for whatever delta, technically for any delta, you can have such stuff, right? For any delta, you choose a delta, you get this. You choose another delta, you get another one. So delta is between 0 and pi over 2. Okay, so this is always correct. This is decreasing function. Okay, now we have this part. This, it doesn't matter you have a small delta and a bigger delta. It works for all the deltas between 0 and pi over 2. And then this one, let's check. This is a positive number, and it's less than this number. You choose this to be the e to negative r sine delta d theta. You choose this constant. It's a maximum constant, and then times pi. This is pi minus 2 delta, which is use pi. Okay, so we have such estimation. So one part, at the two corners, we use the length of the domain to estimate. At two corners, we use length of the domain to estimate. In the middle, we use a function to estimate. Okay, so in the middle, we use a function to estimate. Okay, now let's see. For any, this works for this holds for any delta between 0 and pi over 2. Now let's, for any epsilon, then choose first delta less than epsilon over 3. That's one thing. Delta less than epsilon over 3. Then there is R0. So you fix this delta. Remember, we can allow this R approach infinity. You fix this delta, you let R move, R change. There's R0 such that the exponential, this quantity, exponential negative R sine delta is less than epsilon over 3 pi. So here is also, that's a reason you put pi for R greater than R0. So if R is small, possibly it's not that small, but when R is extremely large for this fixed delta, this it will approach to the 0. This is a negative exponential function. Exponential to the negative quantity. If the negative value is too big, it will approach 0. So for arbitrary R greater than R0. So what? So this, so you have a 2 delta plus e negative R sine delta pi less than 2 epsilon over 3 plus epsilon over 3 pi times pi is equal to epsilon. Right? So this part. Then it gives us this limit equal to 0. It gives us this limit equal to 0. Okay. So this is a tricky process. A tricky process. You cannot estimate the evaluation over the whole interval. If you evaluate over the whole interval, there's no changing upper limit. because over the whole interval you will reach 0. You reach 0, this upper bound will be 1. Then you cannot use the r will disappear. Sine 0 is 0, so r times 0 is 0. So you have to give a little bit of space for r. Okay, so far we show that over the large radius the integral is 0 when you take the limit. Now let's check the small radius. For the small radius, before that, let's study something. So the exponential function, e to iz minus 1 over z. From the real calculus, we know this one has a limit. So it has a removable singularity. Z equal to 0. It has a removable singularity z equal to 0. So it means there is an m positive such that it can be controlled by m for ops value of z less than 1. It doesn't matter, it's less than 1, less than 1/2, it's not important. We just say, oh, in the closed disk, it is bounded. It's bounded. Hence, the integral c little r eiz minus 1 over z dz, it's less than or equal to integral c little r eiz minus 1 over z dz, and this is m, and half of the length of the semicircle, pi r, half, it's the length of the semicircle, so it's m pi r. Then if we take the limit r approaches 0, this integral controlled by r approaches 0, the integral is 0. Integral 0, we need what? We need this integral over the small r, right? And this approaches 0. This one, 1 over z has a whole integral. So the integral over the whole circle is 2 pi I. If it's integral over the half of the circle, it's pi I, right? This is a pi I. The thing is that, is it a positive pi or a negative pi? This time it's a clockwise orientation, so it's a negative pi I. So whenever you integrate along the semicircle for the 1 over z, you will always get pi I, the semicircle centered at the origin. And the only thing is about the sign, is a positive or negative. It's a negative oriented, so it's a negative pi. So this integral is equal to negative pi. Okay, so what do we have? Let's summarize what we have. Right, we spent a long time. Okay, so this is what we got. We have 4 terms. Remember, we have 4 terms. The sum of those 4 terms is equal to 0, because this closed rectifiable curve includes no poles. And we know the first and third terms together give you together give you the sine x over x with the 2i, and we just spend a long time to compute. The second term will approach 0, and the fourth term will approach negative pi I. So let's summarize. We will get 0 is equal to first plus a third is integral r, the limit r approaches infinity, later r approaches 0, and 2i sine x over x dx. And the second term, 0. Fourth term, negative pi I. Okay, so that's what we have. And then we just move this to the other side and divide by 2i. So we get the pi over 2. Okay, so this problem is very long, and sometimes we don't remember what we are trying to compute. We have four terms. Part of them provide the target. Part of them we have to estimate, put the values, or let them vanish. Okay, so this type of integration is always tricky. Let's see if we can get more examples next time, and we will continue. The final exam. Okay, let me say something about the final exam. The final exam, I will give you similarly. I will give you some practice, some problems. It's open book. You can consult the internet. You can consult the textbook or the notes, whatever, or you can find whatever resource from the internet. But you cannot discuss with your classmate. Okay, so we do more computations. Possibly we will do more computation about this application of the residue theorem. It's very, very important. Especially it's important for applied subjects. Okay, it's very important for the applied subject. Sometimes you need some evaluation of special integrals, so you have to know how to integrate some tricky, weird integrals. Okay, we stop here today.